Some of you are asking me some questions about the mathematical representations for this unit. So I want to go through, I had already done number 1 on practice set 2, but I'm going to do kind of a broader view so you can kind of understand these equations a little bit better. The main equation has to do with efficiency, and we dealt with efficiency in the last unit, and especially with energy. Efficiency is how much of the energy in you can pull out. Okay, and it's a percentage. It has no other units because the units of power will cancel. So in all different contexts, you're going to have power in, what's supplied, the rate of energy that's supplied or the rate that work is done, and then you're going to get something out of it. That's the whole point of all these different machines and apparatuses that and devices we've been talking about. So you can have a really basic problem where all you have to do is solve for efficiency or solve for power in or solve for power out if you're given these other variables. So the efficiency is really telling you how much or what percent of the energy gets used. And the rest of it, it's implied, is wasted. It's not being used, so it gets wasted usually as heat, but not always. Okay, so that means we need a way to solve for power out, and we need a way to solve for power in. So we've defined power before. Power is the rate of energy use, so we can call it the change in energy over the change in time. You can also find the amount of work done, because work is equal to the change in energy. When we talk about electricity in particular, we do current times voltage. So there's all these different ways to solve for power, and which one you're going to use depends on the context in the problem itself. So it depends what information you're given. So you might have a car that starts at rest and gets to a maximum speed of 2 meters per second in a minute, and so then you can solve for power that way. You might say you pull your cup with a certain amount of mass up to a height, so that changes in gravitational potential energy. It might be that you can measure the tension force, and you do that for a certain distance. You can measure the work, or you might just use the current and the voltage sensors and get that information. So any of those ways are valid ways to measure power. When we're talking about solar panels, the amount of power is related to the incoming light source. So to this solar panel, right, the solar panel has a width and a length, and that will give you a surface area. So surface area of a solar panel is going to limit how much energy it can take in, right? So this limits how much energy it can absorb. How do you figure out solar area? Surface area? Surface area is length times width if it's a rectangle. So that's pretty easy to do. So how do we figure out how much energy it can absorb? Well, that has to do with the intensity that's hitting it. So there's light coming in that has a particular intensity at the location of the solar panel. So once this reaches this point, right, the intensity that hits that area will give you your power. So intensity is going to be, right, if you look at the units, is watts per meter squared. So if I multiply that by the surface area of the solar panel, which is in meters squared, that's going to leave me with watts. So that's the power that's coming in to the solar panel. And that's going to be in watts. So all these are units. So this is the intensity at the surface of the solar panel. Okay, so this is important also. So this gives you the power in. Now, what if you're not given the intensity at the surface of the panel, but you're given the power of the light source itself? Well, the power of the light source, like you have a 60-watt bulb or a 200-watt bulb, or the sunlight is 750 watts, whatever it is, whatever the power of the light source is, it gets dissipated as it leaves the light source. So you want to imagine if you have, let's say here's the light bulb. When you're close to the light bulb, that power is really, well, I'm going to make like a little cone here. So imagine this light shines and it makes a cone like this big on the ground, right? So here's your light and it illuminates this cone here on the floor. So you can imagine that there's bands around here. So there's a band here, there's a band here, right? And you're illuminating these bands. And as these bands get farther and farther from the light source, it's not as intense. So we need to find the intensity of the light source when it hits the solar panel. So for that information, we need the power of the light source at the light source. So let's pretend this is a 100 watt bulb. That's the power right at the surface here. If we're going to be a distance, right, if this is our distance from the light source, and we'll call this R equals, let's say it's half a meter away. Well, half a meter away, when the light gets over here, it spreads out all that energy, and so we can figure out the intensity at the surface of the solar panel. So to figure that information out, we're going to take the power of the light source and we're going to divide it by the surface area of a sphere. Now, why a surface area of a sphere? Because you want to imagine that surrounding this light bulb is a sphere in 3 dimensions where that energy is getting spread out. So the surface area of a sphere is 4 pi r squared. So these all link together, and it really depends what information you're given in the problem. So you might just you might be given power out, power in, and solve for efficiency. That would be easy. Okay, so that's the most basic problem. However, you might have to solve for the power in by doing this, right? If you solve for the power in, you need the surface area of the solar panel and the intensity at the surface. So that could be given. That might be given. This is the surface area of the solar panel. And I showed you right here how we solve for that. If you don't have the intensity at the surface of the solar panel, then you need the power of the light source and the surface area of a sphere. You need the R, how far away the light source is from the solar panel. Those are the steps that you may have to do to find power in. Power out can be, so let's talk now about power out. So power out might be either current times voltage if you're running an electrical appliance, an electrical load, like a motor, a light bulb, a little buzzer, something like that. However, you might have to do change in energy over change in time. For example, if you're lifting a weight, like we did with our wind turbine, right? If we lift a weight, then you're going to need to do GPE equals mgh. And you're going to need to know how heavy it is and how high is it lifted and how much time did it take to do it. It might be that, you're running, that you're using a solar panel to run a little model car. So if you're moving something, you might have to do your kinetic energy, and that would be 1/2 mv squared. So, or you might, if you're pulling something, you might be doing work. And work is the force, that tension, right? If you're pulling something for the distance that you're pulling it, and that would be work over time. In all these cases, in this case, these three, you need to find time. So this would be your power out. That's what goes on top here. So those are the pieces of this puzzle. And if you think it's complicated, well, yeah, it's pulling together Notice we've got efficiency that we talked about in the last unit a little bit. Power we've talked about, right? Intensity is the only new piece that we're adding in, and we're using it here and here, two different ways we can pull that together. And then power out, we've done. This is from our energy unit. So that's why we do this at the end of the year. It gets more complicated. So these are the foundational like puzzle pieces, I guess, and your job is to put them together in whatever fashion you need to in order to solve a variety of problems. I hope that this helps. I will show you some more examples later.